Hey class, welcome. We're taking a look at our third video in Unit A, which is talking about how to actually do the hypothesis test then for an Anova problem. So let's take a look at our tree example, and I'm just going to take us back to where we first saw that. And it's really important that you watch these first couple of videos, especially this last one, which is talking about how the theory behind the Anova test and how it works. Anyways, this is what we're looking at. We're looking at this guy right here. And so we've got some Alberta, BC, and Ontario trees, and then we've got the heights of the trees. And these are in feet, I guess. I don't know if it really matters what the units are, but they're, let's say they're feet. And so we're asking, is there a difference between the heights of BC, Ontario, and Alberta trees? So the way that we do that then in an Anova problem is we set up our hypothesis this way. So step number one, of course, is always our hypothesis. And for an Anova problem, it's always going to be done the same way. So mu A is equal to mu B is equal to mu O. And remember, the mu that we're talking about here is the height in each case. So the height of Alberta trees, the average height of Alberta trees, the average height of BC trees, and the average height of Ontario trees. By the way, a common mistake that people make when they're starting off here is to do something like this. The average of the provinces is equal to the averages of the heights of the trees. And that's actually just nonsense. That doesn't mean anything at all. Because how do you get the average of provinces? Right? You can come up with the average of the heights, but this doesn't mean anything. The reason why people make that mistake is that if you take a look at a spreadsheet, what you're going to see here is you're going to see the province and you're going to see the height of the trees. And so you're going to have Alberta, BC, Ontario, and so on like that. And then you're going to see, different heights like this. And so people tend to look at that and say, well, then it's the mean of one versus the mean of the other. But you can't calculate a mean for a nominal variable. What we are talking about is the average height of Alberta trees versus the average height of BC trees and the average height of Ontario trees. We'll talk about that a little bit later, but I just want to show you, where we're going to look at that. It's further on right here. So this is what we call stacked data right here. And stacked data is how the numbers come from in the spreadsheet, right? So you're going to have a column for program, you're going to have a column for age. Now, I'm using a different problem here. So this is not provinces and tree heights. This is program and age. But we'll get to this one. But what you do is you sort according to the nominal variable. So this is a nominal, this is an interval variable. And then what you do is you unstack them. So we take all of the ages in this case, and in our example would be the Alberta tree heights, and we put them into a column for Alberta, or in this case program A. And then we do the same with B, and then we do the same for C. So we're actually unstacking them and putting them into three separate columns, where these are the ages in this example for three different programs. So we've done that way back here. Let's go back to our original problem. Right there. So this is unstacked data. The heights already put into underneath the various treatments. Okay, so that's really important in terms of setting up your hypotheses here, is that it's the mean height of Alberta trees is equal to the mean height of BC trees is equal to the mean height of Ontario, against the alternative at least one difference. Number two, the test statistic is, and I usually just ignore this part, but here it is, it's a ratio of variances. The total variation in heights is split into two components: the variation between and the variation within, with an adjustment of degrees of freedom. And the k, remember, is for the number of treatments. So k is equal to 3 in this case. The rejection region is always an upper tail f-test. And so go back to that last video. I'm not going to explain this again, but it's when the SSB is significantly higher than the SSW, adjusted by degrees of freedom, that you end up with a high f-star value, and that actually corresponds to the means being different, or at least one mean being different from the rest. If most of the variation is within, so SSW is a bigger term, you end up with a low f-star value, and that actually supports the null hypothesis. Okay? The degrees of freedom are found like this. So it'll be alpha, and then your degrees of freedom are k minus 1 and nt minus k. And you can always, in an Anova problem, find your degrees of freedom right there. So the degrees of freedom for the numerator and the degrees of freedom for the denominator. And then we do the calculation, and then we make the decision. And then we'll get into this guy, the multiple comparison of means, later. That'll be in the next video. All right, so don't worry about that right now. So let's take a look at the Anova example here. And so let's see what we've got here. Step number 1. HO is that the mean heights of Alberta trees is equal to the mean heights of BC trees is equal to the mean height of Alberta, Ontario trees, against the alternative, not that they're all different from each other, but at least one of the mu's, we'll just call it mu j, differs. And by differs, we mean from the others. I usually just say differs. Step number 2. This is always going to be an f-test of SSB over k minus 1 divided by SSW over nt minus k. 3. This is going to be an f-test, and the degrees of freedom are going to be k minus 1 and nt minus k. So in our particular case then, that's going to be k minus 1 is 3 minus 1. So 3 provinces minus 1 gives you 2. Nt minus k is that there's 12 numbers in total. Minus 3 for the k gives you 9. By the way, those two add up to n minus 1. 2 plus 9 is 11, which is n minus 1, which would be the denominator if you just took the sample variance formula, n minus 1. All right. This is always an upper tail test where you've got an alpha here. So alpha will be 5%. We'll only do examples where alpha is 5% or 1%, unless we're doing this with Excel. So let's go to the table now. And so we're going to go to the F table. Where was that? Just got to grab a little sheet of paper here. Oh, it went fishing somewhere. All right, I'll just go and find it. So it's somewhere around here. Oh, there it is. Okay, good. All right, let's get rid of all this stuff here. All right, so what we do is we take a look at the 5% table. So there's a 5% table, and then there's a 1% table. So we're looking at the 5% table. The degrees of freedom for the numerator was k minus 1. So that is 2. And then the degrees of freedom for the denominator was nt minus k. That was 9. So when we take a look at the intersection of those two, we get 4.26. So that is our critical value. So 4.26, if your f star value is greater than 4.26, we're going to reject HO. All right, by the way, there is probably an Excel formula for this, isn't there? Yes, there is. Let's go down and find it. Critical values for an F distribution down here. An upper tail test is, it's kind of like the chi-square distribution. So it's an, instead of a chi-square, of course, it's an F inverse right tail. And then you've got alpha, and then degrees of freedom for the numerator, degrees of freedom for the denominator. So in our particular case then, that's going to be, and I'm just going to take us back there. So that would be an F dot inverse. Remember, critical values are always inverse functions. Right tail, just like in a chi-square distribution, because this is skewed. And then we've got alpha, and then degrees of freedom for numerator, which is 2, and then for the denominator, which is 9. So that's how we do that. So that's alpha k minus 1 and nt minus k. All right. Now we come to the calculations. So for this, let me just put down some summary numbers here. So the sum of the let's back up here. Let's go back up here, and we're going to take a look at this table right here. Okay, and we've got these guys here. So the CJs are these guys right here, and then the C squared J's are these guys right here. And I'm just going to put those down here. So the CA, the CB, and the CO values were 178, 331, and 349. And then the CA squared values and the CB squared values and the CO squared values are 79, 74, 27, 585, and 31089. And this was from page A6. And I'm just going to take you back here again to show you, because this was in the last video. So what we do is, let's just take a look at these guys here. These are the original numbers of the tree heights for Alberta. And if we sum those up, that's the CA value. And then if we square each of the numbers, so 40 squared is 1600, 2500, and so on like that. If we square each of those and we add them up, then we get this guy, which is the CA squared value. And again, that number is not 178 squared. It's not the square of the sum, it's the sum of the squared values. And we do the same then for the other two treatments as well. So those are the summary numbers there. Now from there, we can take a look at these formulas, which you're going to find on page A6. And so on page A6, we have that SST is equal to the sum of the CJ squared values minus the square of the sum of the CJs over NT. So that's going to be equal to 7974 plus 27,585 plus 31,089 minus 178 plus 331 plus 349 squared over 12. So these guys here are these guys, the squared values. And then these guys here are just the original values, the sum of the original values here, okay, for each column. So that's what it looks like. And this comes to, what do we get here? 5301. And all 5301 is it's just the numerator of the variance, the sample variance of all 12 numbers together. The heights of all the trees. Okay? That's all it is. Now, SSB is equal to, and again, we're taking this formula from page A6. You take each column, its CJ, and you square it, and you divide through by its NJ. And you do that for each one. And then the last part is exactly the same as we had above here. So it's the same as this right here. So when you're calculating this with a calculator, store that somewhere so you don't have to recalculate it. So what we've got here then is it's 178 squared over 4, because there was 4 trees in Alberta, and then plus 331 squared over 4. These all had 4 for an n. And then the same last term here. So this is 178 plus 331 plus 349, all squared over 12. And that gives us something exciting. Let's see. 4414.5. So this is your SST. This is your SSB. Your SSW will be the difference between the two. So that's going to be 5301 minus, 01 minus 4414.5, and that equals 886.5, and that's your SSW value. All right. Now what we do is we calculate the F star value. So the F star then is going to be the SSB over K minus 1 over SSW over NT minus K. So that's going to be 4414.5 over 2. That was k minus 1. And in the denominator, we've got 886.5 over 9. That was nt minus k. And when the smoke clears, you end up with 22.41. Now, we come back over here and we say, where does 22.41 fall? And it is way out here. So 22.41 is way out there. So we would say 22.41 is greater than 4.26. Therefore, reject HO. What this is telling us then is that at least one of these means differs from the others. The next thing that we will do, which we'll do actually in the next video here, is to find out, well, which ones actually differ. And we're going to take a look at each pairing. And we're going to use a confidence interval to look at the differences of the means. So this is called the Fisher's least significant difference, or LSD, or multiple comparison of means. And we will talk about that in the next video. But just before we leave this video here, how would you calculate a p-value? Well, a p-value would be an f dot dist dot right tail, and then your computed value, and then your degrees of freedom. So remember, so this is a p-value. And so remember, a p-value is always a dist function. Right tail, because we're always going up in an Anova test. This is your f star value, and then k minus 1 and nt minus k. And just to show you that, let's go over to here. And it's going to the p-value page. And so we're taking a look down here at the f distribution for the upper tail, and that's what we've got there. F dot dist dot right tail, your f star, your degrees of freedom for your numerator and for your denominator. So that's what we've got. So that's how we do that. We are not actually done with this problem here, because we have to find out which mean or means differ from each other. And that will be in the next video. So I'm going to end the video here. Thanks for watching.